So hello, we'll start our course on foundations of fluid mechanics. This is an introductory course in fluid mechanics where we are going to learn about fluids, what distinguishes a fluid from other states of matter, learn about governing equations for fluid, primarily from the point of view of conservation of mass and momentum, and then go about actually trying to understand various problems which we could look into using those equations of fluid motion. So before we get started with developing equations for fluid flow, it's important for us to understand what is a fluid. Fluid is something in a sense that is very visual. Any flow is extremely visual. There are a lot of disciplines in engineering where we use the byproduct, we use the end product in our day-to-day life. The applications are visible, but the actual physics is not necessarily visible to us. Flow physics in contrast is something for which you may not necessarily be interested in the end product, but they are all around us. And as you will see, it's all pervasive. It's omnipresent in terms of how they make an impact in our day-to-day life. So we'll in this lecture, we are going to start with where you might have been prior to this course, which is having some basic idea of rigid body Newtonian mechanics, and then from there we will take a leap to what fluid mechanics actually is and how is it different from the rigid body mechanics that you might have done earlier. Then before we get into looking into motion of fluids and looking into flow physics itself, it's important to do some preliminary background in how we distinguish phases of matter when they are in a static state and then when they are under some external forces, the dynamic state. And this is where we will see things will start to get blurry. We are going to challenge our intuition of what we call as a fluid, what we call as a solid, and as you will see that this brings about a certain degree of fuzziness where a lot of things which you might have earlier thought of as not necessarily as a fluid object does indeed flow. Then before we write down our governing equation, it's important to actually take a pause and ask ourselves a question that a gas that is there all around you, which is what is an example of a fluid, is made up of gas molecules. We know that from our elementary understanding of what constitutes the air around us. So if it is made up of oxygen, nitrogen, carbon dioxide, traces of other gases all around us, then how are we dealing this or how are we treating this as a continuous medium? What assumptions lie in treating this as a continuous medium? And finally, we will conclude by saying that a lot of tools that we are going to learn in this course, a lot of modeling techniques that we are going to learn in this course would carry over to fairly different scenarios that are not the typical fluids. So we'll see that we are not going to get into developing models for those systems, but the notion of flow can extend to systems which are well beyond our imagination of what we think of as fluids. So with that, let's get started with our lecture. And the appropriate way to start this is do a recap of what you already know from your 12th standard physics projectile motion. So if you throw any object under the action of gravity, we are familiar with the fact that this is going to execute a parabolic trajectory. There is only gravity that is acting on this object. So if you apply Newton's second law and ignore for the time being any role of friction from the surrounding air, then this executes a very nice parabolic trajectory. Now, if the object was not a point mass and instead if you were to throw this pen which is there in my hand, I mean a model of, if you think of it as a rocket or a missile, this would have 6 degrees of freedom, 3 translational degrees of freedom, and then there would be 3 rotational degrees of freedom. So nonetheless, you can basically predict the trajectory of each of these objects given the initial velocity, given the initial angular velocity, and then saying that if there is no external torque acting on the system and the only external force is the weight of the object, you would manage to actually obtain the trajectory of this particular body. It's a fairly straightforward approach, and you would have definitely done some version of this for simplified point particle object. Now, if you think of a similar example where unfortunately you have spilled tea or coffee. Now, this is again also driven by gravity. It's gravity which is actually responsible for this splash that you are seeing. Now, how much soever unfortunate this may be, do you model them just like how you modeled the previous problem? If you want to find out that how much would this splash spread, these tiny droplets that you are actually seeing, how many of these droplets are going to form? Would this splash actually spread over a certain distance that is independent of how much volume of coffee was there in the mug? Would it depend whether if it was not coffee but it was water? So how would these things be captured? Do you go back to the same question saying that, well, this is also Newton's second law, and if I now say that I am going to basically apply this about the center of mass of this object, is that helpful? Does tracking the center of mass of the splash of coffee is helpful in actually identifying what's going on? And the answer, you don't need to know any detailed math, the answer is clearly no. Tracking the center of mass is not helpful in an exercise like this. You need to actually get a feel for how this entire body, the entire shape, how is this actually moving around? So, the aspect of tracking a center of mass or tracking a rigid body starts to become very different the moment you start thinking of flows around you. These are deformable medium. So there is deformation that is going on. The shape that we have drawn here, this is an instantaneous snapshot. If you were to take the picture a few timestamps earlier or few timestamps later, it would not look like this, it would look something else. So there is a continuous deformation that is happening, and that's what we want to say here, that fluid mechanics is a study of deformable continuous media. So it's a subset of the broader field of studying deformable continuous media, and because it is deformable and because it is continuous, what we need is, instead of a few coordinates describing the center of mass of the object, what we need is entire fields of velocity, density, pressure, and maybe few other quantities. But the important point being made is that we are interested in fields. We are not interested in a single point description. This is where the departure starts, and this is going to be where we will close this lecture, asking in the end that when can we define this to be a field? And this will then lead to our classical Newton's law will get an upgrade. We are still going to study Newton's law. This is not something which we are disregarding. We are going to frame our Newton's laws of conservation of momentum into a partial differential equation for deformable media, which would be known as the Navier-Stokes equation. This is going to come few weeks down the line. But this is the essence of what we are going to do. You are still going to apply conservation of momentum, you are still basically going to apply conservation of mass, and then you will say, hang on, this is to be done for something that is deforming. If the object is deforming, I am incapable of describing it just based on few fixed points. I need to get the picture of objects continuously in space. So, as a recap, what you have done in your rigid body Newtonian mechanics, you had 6 degrees of freedom, translation and rotation. Now you have infinite degrees of freedom because you are describing quantities which are fields. So you have them described at every point in space. Earlier, the unknowns were its position and angular velocity. Now you have the velocity field, density field, pressure field, temperature field, and in some cases you may be interested in other things like, let's say, concentration field, a bunch of different quantities, but everything is a field. Previously, your Newton's law for translation and rotation just said that mass times acceleration is equal to sum of all external forces. Moment of inertia times the angular acceleration is equal to sum of all torques acting on the system. These are bunch of ordinary differential equations. They could get a little more tedious if instead of a point you are trying to track, let's say, a frisbee. I mean, I'll give it to you that it's not a very trivial calculation to do for more complicated shapes. But still it remains an exercise in solving ordinary differential equations. Whereas now the governing equations are going to be a partial differential equation. At this point, this equation that I have flashed here, I have not shown you how we arrived at this equation, but this is going to be an essence of something that will come few weeks down the line, where we are going to derive this equation. This equation, by being a partial differential equation, describes point-wise balance of momentum. And similarly, there will be a version of point-wise balance of mass. Things can be moving through that point, things can be entering, exiting through that point, but you are looking at a point-wise application of conservation laws. And as an example, we saw the example of projectile motion, and obviously as I am saying that you can have various things, you can have flow past an aircraft wing, which is where you would be applying the laws of fluid motion. And this is where the point I made at the beginning, that this is all pervasive. If you are watching this video in the month of August, in most parts of India, you may have been battered by monsoons. So the monsoon winds, the southwest monsoons that are probably hit most parts of the country, that's a fluid motion. The flow inside in your aorta is also a fluid motion. The coolant in a nuclear reactor, that's a fluid motion. And even something as massive as the giant red spot on Jupiter, that's also a fluid motion. And all of these are going to obey the same equations as that is given above. That's the beauty. You are looking at things which are wildly different. It seems like they cannot be as different. I mean, how are we talking about a motion that is happening inside your blood vessel to the giant red spot in Jupiter? How are the monsoon winds basically connected to the lubricant that is present inside your car? But yes, they are governed by the same fluid equations. The only difference that comes about would be in their boundary conditions, would be in the values of the material properties, density, viscosity, and other things. This is where there is a universality in how we approach things. We see them everywhere. We see them in various different scenarios. As I'm speaking, I'm breathing in air, I'm breathing them out. That's a fluid motion. But the difference is only going to be there in terms of the material property. So what do we actually mean by a fluid? We say that water flows. You don't need a course in fluid mechanics to make that statement. You also know that honey flows. You also know air flows. These are like obvious, trivial statement. And you would also be able to infer that the table, the wooden table on which I'm resting my hand, doesn't flow. So what precisely distinguishes them? So this is where the fact that we are talking about deformable media, that's the important word, or deformable continuous media, we make a distinction between solids and liquids. So when you say, I'm trying to push a solid sideways, so you are trying to, let's say, if you have an eraser in your hand and you try to give it a push on the top of the eraser, it's going to deform. You can see that deformation. And it stops. It doesn't. If you have given it a particular push and you have held the eraser, you will see that deformation. You release it, in most cases it's going to spring back. Whereas for a fluid, it's going to continuously keep moving as you keep pushing or as you keep giving that force on the fluid. So a fluid, this is first we will define what the working definition is for a fluid. A fluid is a substance that deforms continuously. That's the important word. It deforms continuously under any applied shear stress or under applied force acting on it. What shear stress? So I have a fluid, imagine the two palms of my two hands confining the air in between. As I am trying to keep one hand fixed and I keep moving the other one, that's called as a shearing motion. So when you do this shearing motion, I am basically making the air in the gap move. Now you would not be able to see that because that deformation is not visible for the air that is there. But if you were to do it for a fluid where I could hold the fluid in between two plates, slightly more viscous so that it doesn't spill over, then you can actually see the deformation. If you put a small blob of dye, you will see the dye deforming. And this can be howsoever small a stress that you apply, it's going to continuously deform. And it doesn't recover its original shape on release. So we are going to come back and quantify this clearly. So we'll make this mechanically precise in the few slides, but first we need to understand from three complementary ways how do we distinguish water and air as fluids from solids from their molecular makeup. Their molecular structure, basically how does it make it different. So there will be a thermodynamic picture, there will be an energetic picture, and then finally we will have a mechanical picture under the action of an external force. Thermodynamic picture. Again, I am borrowing on things which you might be familiar with. This is the pressure temperature diagram. In the PT plane, materials will usually occupy distinct regimes. They can be in a solid state, they can be in a liquid state, they can be in a vapor state. And there can be a triple point and there can be a critical point. Now, knowing the pressure and the temperature fixes the phase. And we have a feel for this for simple materials that we are accustomed in our day-to-day life, like water, ice and water vapor. Now, how do they look when we probe in terms of their structure? If you were to probe a solid, and especially I have taken here an example of a crystalline solid, the atoms or molecules are going to be very nicely ordered. It's like students sitting in a class on their respective benches when the lecture is going on. A liquid is when these molecules are a bit out of their ordered state, but they have not yet completely gone into a fully disordered state. Whereas a vapor is going to be the most disordered state, where the class has ended and everyone is basically scooting off and going to wherever they have to go next. So you can think of that liquid occupies this intermediate structural state from solid and vapor. Solid, the most ordered state, vapor, the most disordered state. And liquid is going to be something where it is in between. Now, can we probe this? So there are different ways of probing this. So you can see what is there inside. Now when I say see what is inside, that sounds a little funny, because how do you see what is there inside water? How do you see what is there inside a gas? How do you see what is there inside the solid phase? So one of the ways to see is you send in X-ray, and the X-ray is basically going to get scattered, and you collect the scattered signal, and from that you try to actually find out what is the distribution of neighbors. So let's say that there was a molecule that was sitting at the origin. Now with respect to the molecule, that particular reference molecule, where would its neighbors lie? Now if it was in a crystal state, all its neighbors are going to be at some very definite distances away. So the quantity that I am plotting here, this is basically known as the paired distribution function. It's in a way a measure of what would be the probability of finding a neighbor at a certain distance from yourself. So it's in some ways related to that kind of a probability. So as you can see, if it is crystal, I know definitely where my neighbors are located. I have a certain very ordered arrangement in which R being the distance from the center of that particular atom or molecule. For a gas, I cannot have a molecule coming and occupying where the reference molecule is. That's going to basically violate. I mean, if you are sitting on a bench, assuming no one comes and gets to sit on top of you, then that space is excluded. Your location on the bench is excluded for all your classmates. Now, if everyone in the classmate was in the class, all your classmates were randomly moving around, the probability of finding a neighbor at any distance would be the same. It doesn't matter. As long as they don't come and sit on top of you, you can find a classmate anywhere because they are all in a highly disordered state. But if you do this for a liquid, you don't see something as ordered as a crystal. You don't see something as disordered as a liquid. Sorry, as a gas. Instead, for a liquid, what you observe are these peaks and troughs which gradually shallow down, and you get a state which resembles at a large distance approaching a constant value, but there is a loose sense of order that is there. It is not as disordered as a gas, it is not as ordered as a crystal, but there is a sense of some kind of preferred distances or preferred shell that is actually there. And these are things which you can get out of experiments. These are static experiments. So you can do what I just said. You take any material and you want to probe the structure of the material. Just like when we have a fractured bone, we do an X-ray and we try to figure out what has gone actually wrong there. In the same manner for materials, we send in X-ray and looking at the scattered signal from the X-ray, we try to perceive what is actually present in there. It works on the same principle. So any new material that you discover, you synthesize a new material in the lab, you come across a new material and you want to find out what is the structure inside this material. You perform an experiment like this and you try to find this kind of a diagram. This is basically known as finding the static structure or the pair distribution function for that particular material. Now, why does this happen? Why do you see these kind of sharp spikes for crystals and almost nothing for a gas? And this is where the answer lies in the energetics. So if you say, I have a gas molecule, and this gas molecule, with respect to this gas molecule, I try to find out. So I label this molecule as A, and I have another molecule which is labeled as B. So these two gas molecules, if there is nothing that acts between them, there is no force that is acting between these gas molecules. So you are talking about what is known as an ideal gas. And you are looking at a dilute scenario where each gas molecule, they are freely, merrily moving around, and they can freely, merrily move around till they come in contact with another gas molecule, after which they undergo a collision and they get deflected and they move elsewhere. So there is a contact or there is a force that is experienced only when they make a contact, only when collision occurs. Unless there is contact, unless there is collision, there is no force that is acting. Which means that the potential energy, because if you write this force as a gradient of a potential, then this potential energy barrier is going to be infinite. It's going to be infinitely large for a gas molecule the moment you are within the excluded volume. What is excluded volume? So let's imagine the radius of this molecule is Ra, the radius of this molecule is Rb. So this excluded volume will be Ra plus Rb. Because when it has come to distance of Ra plus Rb, the two molecules are touching with each other. They cannot overlap. So you will get this kind of a hard sphere, what is called as a hard sphere potential, where there is an infinite barrier. You cannot overcome that barrier. Hence, you need to stay anywhere outside. Now, real materials are not exactly hard sphere. The barrier does exist, and the barrier basically comes from a short range repulsion, which means the barrier basically gets smoothened out. So you have now a smooth barrier, and obviously it's getting prohibitively difficult as the second molecule is approaching the first molecule. But then there is also something that happens when distances are far away. When distances are far away, there is something called as a van der Waals attraction. There is a long range attraction that exists between the two molecules, and this basically comes from the fluctuating dipoles that are present in these molecules. So there can be a van der Waals attraction which will exist when the materials are far apart, or sorry, the molecules are far apart. Now this gives you what is called as an energy landscape. The energy landscape has a short range repulsive barrier and it has a long range attractive tail. Which means if you have something, because you can see this is the quantity which is the potential. So when you write down the force is basically going to be negative of the gradient of this potential, which means you are going to get an attractive force at large distance and a repulsive force at short distance. Now when you have a potential which basically has these two different kinds of branches, you are going to get a potential minima. There is going to be a potential minima that is going to exist with reference to a datum. Now why is this minima important? Why is this barrier actually, the height of that minima or the height of that well, actually so important? Because if you don't have any other energy to compare with, this is not a relevant quantity to talk about. You can have a very deep well, you can have a very shallow well. So you can have a potential well which looks like this, or you can have a potential well which looks like this. Why are they of any difference? Why does it matter? Because there is also an additional energy that is related to thermal fluctuations, and this is order kBT. So at a given temperature, the molecules are basically constantly executing a certain thermal behavior, and this thermal fluctuation gives you an energy scale which is kBT, kB basically being the Boltzmann constant and T being the temperature in absolute units. So now you can compare the depth of the well vis-a-vis whatever is the thermal energy scale in the problem. So if the thermal energy scale was extremely small compared to the potential energy well depth, you are going to get a liquid, because the thermal fluctuations are extremely weak and you are not exactly able to move out of your nice crystalline arrangement. In contrast, if the thermal fluctuations were very large, such that they were much larger than the energy well depth, in that case, the energy well depth is insignificant and you can freely move around, and that is what would be a gas. Sorry, this should have been a solid. So if the thermal energy scale is much smaller than the potential energy well depth, you basically get a solid, a nice ordered arrangement of your crystal. Whereas if it was a gas, then it's insignificant. That long range attraction which is dictating that depth is no longer going to compete anyhow with the thermal energy fluctuation. And when they are comparable, you arrive at what we call as liquids. So as you can see that there can be this nice classification which is based on the magnitude of the depth of the well divided by the thermal energy scale. These are two energies, and whichever energy wins decides what condensed state are you going to be in. So with this, we now have a very nice picture of what the static state is and why it is this way, like what brings about this particular static state. So large thermal energy, kicks dominate, attraction invisible, you have free flight, and that's your gas. Small thermal energy, they are trapped in wells, tiny vibrations only, and you end up getting the most condensed phase of all, which is a solid. And when thermal energy and the potential energy well depth are comparable, the kicks and the attractions become comparable, and you get a dense but mobile state, which is a liquid. And this is again like as per your intuition, you heat an object and it gets to a less condensed state. You take a phase in liquid, you increase the temperature, it goes into a gaseous state. So what is happening by increasing the temperature, you are providing more thermal energy to the system. And the internal structure of the potential energy well barrier that you have, that can be overcome by providing more thermal energy. So this was the story for the static state, but then this brings about a point that if the same equation governs flows, is there something that becomes fundamentally different? And this is again going to be a part that is quite crucial in terms of what we have. We said that they are all the same physics. So you can start from the smallest scale, and the smallest scale that is quite relevant to us. We are all aware of this term that our gut has a very rich flora and fauna. So that, which basically means that the bacteria which resides in our gut, if you have the good ones, they keep you healthy and strong, and if you have the bad ones, they basically make you fall sick. And if you take one of those residents in your gut, which is E. coli, this is typically something that is micron size. And if you were to compute a number which we are going to encounter a few weeks down the line, that gives us a measure of how strong is inertia with respect to the viscous forces, that would be around 10 to the power minus 5. And as you scale through blood in a capillary, glass of water that you are drinking, stirring it out, one of the fastest swimmers on the planet gives you a Reynolds number of 1,000,000. So as you can see, the bacteria swimming inside your gut and the fastest swimmer, they are separated by this number over almost 11 orders in magnitude. Air over a car, the circulation in the Indian Ocean, 12 powers of 10, and Jupiter's red spot, which is around 10 to the power 13. All of these are governed by the same physics. All of these are basically governed by the same fluid mechanics problems that we are going to study. And the dimensional numbers that we have in this regime, it tells us whether we are in a low Reynolds viscous dominated regime or we are in a high Reynolds number regime. So when we are thinking of this motion being low Reynolds, high Reynolds, we are now basically thinking in terms of forces basically being applied. We are thinking of motion. We have come out of the static state. So once we have quantified that, is the motion very impressive or is the motion actually not that impressive? What is the response of the material to that force that is driving the motion? So if you apply a shear stress and you measure the deformation and you take the same crystalline structure of the molecules in a solid, you are going to find that they are all these points. You can think of them as molecules, or you can think of them as you have marked it out. So you take that eraser example that I said and you take a pen and you nicely mark out points on the eraser in this kind of a grid or lattice structure. Just take a pen and just put dots in this lattice structure. Deform the eraser. You would see that each of those points that you have marked out form this kind of a trapezoidal shape. And if you release it, they come back to the original state. That's the property of what we call as a Hookean solid. Hookean comes from the fact that it's like a spring that we know, where you have learned Hooke's law, that the force that it experiences, the spring force, goes linearly with the deformation. Since we are dealing with a continuous medium, this tells us that the stress that is experienced by the object, which is the force per unit area, is proportional to the strain that is accumulated in the object. So tau being the stress is proportional to the strain gamma, and G basically being your shear modulus. So you would see a behavior where tau plotted against gamma is a straight line where the slope is the shear modulus. Now real materials might deviate from this kind of a linear behavior, but the basic idea being that there is a stress or internal response in the material which comes about due to the deformation in the material. Fluids, which we had said is something that is not as ordered as a solid. It could be a liquid or it could be a gas, the most disordered state. And now you do the same exercise of shearing them. When you shear them, they move to different locations. And as you maintain that shear, they continuously keep moving. So that example that I said, you have your palm, the top surface, you apply a force that is basically making the surface move. You apply a constant force in the tangential direction. The fluid is going to continuously move. In the fluid, the stress that is built up is proportional to the rate of deformation. We'll write these things down formally later, but here, just while we are discussing this, gamma is the deformation, which you can think of it as the initial distance between these 2 points, if I say is delta x, and if I say now the 2 points are basically separated by a distance which is delta x prime, then your gamma would be the ratio of the 2 lengths that are there. It's a non-dimensional quantity. Rate of deformation is the rate at which this deformation is changing. So it has units of inverse of time. So for a fluid, the stress that is there, the internal stress that is built up in the system, is proportional to the strain rate or the shear rate or the rate of deformation. There are different names that you use, and we will make some distinction between them in later classes, but right now you can think of them that it's the rate of change of how much you are deforming. The actual deformation is not important, the rate at which you are deforming is important. And that constant is the viscosity of the material. So this is where we come back to this particular point, that does a system necessarily behave as a solid or a fluid? And there is one example, a live example. Some might say this is probably the most boring experiment because of the time that it is actually going on. This is an experiment that is in operation for 96 years now. And the objective is very simple. You have poured coal tar, hot pitch, into a sealed funnel. The stem was cut and you wait. That's all. You wait and you watch. And then you ask, is this a solid or is this a fluid? And as you observe that Initially, there is a bulbous end that forms, which gradually grows and then it drops. So the first drop fell in 1938. The next one, 47, around 8 years later. 54, 7 years later. The ninth drop was 12 years back, and it took around 13 years for it to fall from the previous one, which was the 8th one. So you might be in luck if you watch. This is a live experiment you can watch. As I said, the live experiment is pretty much nothing happening for all instants of time, and other than that boop when that drop falls. So based on the data, it's likely that the 10th drop might fall anytime soon, maybe while even you are watching this lecture. So this gives you a point that things can be solid-like over minutes, but over decades, it's a fluid-like object. So the answer, so in the previous slide I was discussing that solids are going to deform, and the stress that they accumulate depends on the amount of deformation. Fluids are going to have a stress that is going to depend on rate of deformation. But the world is not made up of perfect solids and perfect fluids. And this is again an example. Here the object, for all you care, if you were just performing an experiment and you were saying that due to gravity, what happens to this pitch? If you observe it over few days, nothing happens. If you observe it over few months, again nothing happens. It behaves like a solid in that particular case. In this case, a very highly viscous solid. It's only when you observe it over decades, which is a long period of time, but still something that we can jot down and make notes of the data, you observe it behaving like a fluid. So this brings about a number. We are not going to discuss this number any further in the course, but it is important to be aware of this because not all of you might be doing courses in polymeric liquids, non-Newtonian fluids or similar courses where there is a number that is defined called as the Deborah number. It's a number which tells us that what is the time scale, the relaxation time scale of the material divided by either the flow time scale or your observation time scale. So if you think of objects like air, water, they are obviously fluid. Why? Because the relaxation time scales are extremely small. It's around 10 to the power minus 10 seconds. For air, you can actually say that the relaxation time scale would be the mean free path of the air molecules divided by the characteristic velocity of air molecules. So the time scale is so short that you are going to never observe a behavior that would be probing that time scale. Your time scale is much larger than that time scale. So the Deborah number in that sense is very small and you see a fluid-like behavior. The example of pitch that we saw earlier or even honey, you can have a relaxation time scale that can be quite large, in which case on shorter time scales they can appear like solid but they can have a slow flow. Glaciers, they have a very large relaxation time scale. So they would appear, if you just happen to visit a glacier and you look at the glacier, you would say that this is a solid. I don't see anything happening in the glacier for the full day that I was spending or camping there. So they appear rigid to us. But if you observe them over years, you are going to see flows. Earth's mantle again has a very large relaxation time scale. So when there is an earthquake, they behave like an elastic solid where the waves propagate. But they are a fluid-like behavior on geological time scales. We know the motion of these mantles and we know that this is actually responsible for the continents to move. Again, an example which relates to our day-to-day life is glass. You will definitely have something that is made up of glass around you, and it would be shocking if you think that glass is a liquid. You would always say glass is a solid. But there are many claims that in old cathedral windows, the bottom is actually thicker. And this is basically coming from the fact that it's slowly flowing and accumulating in the bottom. So, in fact, at room temperature, you are going to see in your observation time scale, based on this Deborah number, you can actually start asking questions that would I be observing a solid-like behavior or would I actually see a liquid-like behavior? So this is a number that's quite useful if you were to probe material and study fluid mechanics of material which are not going to behave in the traditional sense. We aren't going to come back to this number, but it's important to be aware of how we interpret, because the world is a fuzzy spectrum between solid and liquid. Most material lie in the, they are lying on that spectrum. They are not exclusively solid or exclusively fluid. So this brings about now the question of, when we are thinking of modeling this, if you again go back to the example of the air that is all around you, made up of oxygen, made up of nitrogen, and made up of water vapor, carbon dioxide and other trace gases. Everything is made up of some molecule. So why don't we just say, let's just apply Newton's laws of motion to these individual molecules, study their behavior, and then do a conservation of momentum. Fair point. Can be done. There is nothing wrong in it. There is absolutely a perfectly legitimate statement. Let's check how realistic is this. If you say 1 mole of gas, which is around 22 liters of that gas, it contains an Avogadro number of molecules, 10 to the power 23. Tracking the Newton's laws of motion for all these 10 to the power 23 molecules is impossible, and more importantly, unnecessary, because we are not caring about a particular tagged molecule. You put a number on one of those nitrogen molecules. Do you really care of what is happening to that particular nitrogen molecule? Why does it matter? That's not of any significance to us. What is significance to us is how much pressure is that nitrogen exerting in the cylinder in which we are carrying that nitrogen. The walls of that cylinder, which we need to basically make sure are strong enough to actually contain that nitrogen, is something that where the pressure is important. So we care about the fields, which is going back to density, velocity, pressure, temperature, and in some cases few other things. But they are fields, which means they are smoothly defined in space at every point and at every instant of time. Now how is this possible? If I am saying that the air, let's pick nitrogen as an example, the air is made up of nitrogen molecules, then I can have a nitrogen molecule where I am pointing my finger. I may not have a molecule where I am pointing my finger, right? There is no guarantee that I am going to basically see a nitrogen molecule at some point I point towards in space. So for this, you have to ask, how is density being defined? We say density at a particular point in space, at a given instant in time. But density is going to be a volume average over a sampling box, which means you take a sampling box, delta V, you construct a small volume and you take this delta V and you start shrinking it, and then you try to compute this quantity. What is the mass of molecules that is contained inside this particular volume? And this shrinks to a size which is large enough to contain many molecules, but it is small enough such that it looks like a point on the flow scale. What is flow scale? So if I am thinking of designing a pipe to transport water inside my house, at the scale where I am observing all the motion, there is a point that I can mark, and that point should be able to define that. I can define a flow rate, I can define a velocity, I can define a pressure. So I shrink this delta V such that I can define a point, yet it is large enough, which means that this volume is large enough such that it contains many molecules. So if you were to compute this and you design that cube of side L that I had in the previous slide, then with the number density that is there of air, the number of molecule per unit volume times L cube. So as you keep increasing L, you think of 1 micron size volume. You're using an instrument to measure density. What would be the least count of that instrument? So if 1 micron is that small size of that volume that you have, then you are basically going to see an N which is around 10 to the power 10, the number of molecules. So the number of the fluctuation that is occurring in that volume. So what you are saying here is that, let's draw this in slightly more legible manner. So there is a molecule that enters here and then there is a molecule that is exiting. So now, how would the fact that if I am trying to find out what is the average number of molecules inside this box, that average number, that average that I am basically going to calculate will obviously be dependent on the fluctuation that I am having in that number. And that fluctuation is basically going to die down as I go to larger and larger number of molecules. If I have a classroom with 50 benches and each bench can accommodate 2 students, and the lecture was very popular, which means that give or take there were 70 to 80 students always in the class with a full capacity of 100. So I can give an average saying that the average class strength is somewhere between 75. Does it mean that the same students are appearing every day? Does it mean that the same benches are being occupied every day? No. There are some fluctuations. On one particular day, you probably had the right corner of the classroom being empty. Everybody wanted to sit on the back. On a particular day, maybe the back row, the fans were not working and it was completely empty and everybody moved towards the front. But you got an average which was not changing by a lot because the numbers that you are dealing with is reasonably large. Contrast this to a class which is not that popular. People find it boring. In that case, if there were only 10 students in the class which has a capacity of 100, the moment 2 students decide to skip the class or bunk the class, the averages are going to wildly fluctuate. There is a big variation that you are going to observe, and that's exactly what we are trying to say here in the context of molecular behavior. When the system sizes start to become small, molecular fluctuations become so intense that you cannot design or predict something like a field. If you want to say the density at a particular point is 1000 kg per meter cube, if you want to say the velocity at a particular point is 0.7 meter per second, if you want to give a value of pressure as 1015 Pascal, you cannot make those statements if your system size becomes very small. So you need to be in a sweet spot. And this is what you are seeing. As the system size basically goes further and further down, the fluctuations that you are observing goes from 1 in a million to almost 20%. Smaller system size, so which means if you have a carbon nanotube, you have to be careful in treating that system as a pure continuum. On the contrary, most of the other systems that we are dealing in the macro scale, they have significantly large system size. And so when you are doing that sampling volume to decide what is continuum, you are really making a very small error due to the fluctuations that are coming about from the discrete nature of the medium. Every medium is discrete. Continuum is something that we are making an assumption about the discrete nature by exploiting the fact that it is always a large number of molecules that reside in the smallest sampling volume that we choose. In reality, nothing is continuous, everything is discrete. The table on which I am resting my hand is discrete. The mobile phone on which you are watching this is discrete. Everything is discrete. But treating it as a continuum is not a bad approximation. It's in fact in many cases a very, very good approximation. And that comes about from the fact that you are dealing with systems with a huge number of constituent particles, relying on the fact that your sampling size is sufficiently large. So with this, for dilute gases, where if you write down what's the mean free path, that's the distance that a molecule travels before it collides with another neighboring molecule. That's around 100 nanometers. The speed of sound, which is the speed with which these molecules are going to travel, would be around 300 meters per second. So the collision time, the time it takes between two collisions, is around 10 to the power minus 10 seconds. That's what we were seeing earlier. So when you are trying to write down where the continuum Navier-Stokes is safe, you need to say this in terms of flows for which the length scale is much larger than the mean free path and the observation time scale is much larger than the collision time scale. There is in fact a number known as the Knudsen number, which is a ratio of the mean free path by the system size that you are interested in. So when this number is actually very small, you have the continuum theory, which is where our course is going to reside. Then we can have a scenario where you can have slip. You will then have a transition region, and then finally you can have a free molecular region. So very small L, as I said, carbon nanotubes, classic example, rarefied atmosphere, re-entry of spacecraft, flow through tight pores, shell gas flow, MEMS pressure sensors. These are all scenarios where L is actually quite small. Or you have very large gradients. So you can have shock waves, where there is a thickness of the shock wave that becomes comparable to the mean free path, the triple point contact lines, transient events that are happening below the collision time. So the main point is that between doing this in a continuum picture and treating everything as an individual molecule, there is also something that is there in between. Solving Newton's second law of motion for all the 10 to the power 23 molecule is one absurdity which we cannot handle and which is in many cases not necessary. Navier-Stokes equation, which is the full continuum field description, is something that we aspire for and we hope it works for the scenarios we have in mind. But there is also something that lies in between. It's going to be outside the scope of this particular course, that's solving these things in terms of what is known as a Boltzmann equation, where you are solving for distributions of molecules being present in a particular point in space, moving with a certain velocity at a given instant in time. In the continuum limit, this basically turns into your Navier-Stokes equation. Now, as I promised in the beginning, this all can be applied. The machinery that we are learning can be applied to any collection of units, provided averaging over many units is meaningful. You can talk about bacteria swarming, individual bacteria trying to create a collective motion. That's what is known commonly as active fluid. The avalanches that are happening, the granular flow, that's also modeled as a fluid flow. Something that is absolutely beyond our imagination, the beautiful behavior of flocking of birds. Starlings are these birds, and they are not just visually amazing, but there is this murmurations that they create. You can watch these videos endlessly, and the patterns and everything that they are creating, and that's also can be thought of in this continuum spirit. And finally, something when you see these, you can spend endless hours watching drone footage of herding of sheep, and you can see that there's almost like a flow-like behavior that happens. So the tools that we are learning of conservation laws, they can also be applied to a lot of very different kinds of scenarios where they are not typically to be thought of as an air, water kind of medium. So something I'll leave you with, these are small calculations that you can try out. A simple point is the flow over a cricket ball. You know, a typical size of a cricket ball is 7.2 centimeter. The mean free path is at 1 atmosphere, 288 Kelvin is around 700 nanometers. What would be the Knudsen number? Microchannel chip, 500 nanometers. You have gone further down in scale. What would be the Knudsen number? And you can start to get a hint, where do you think the violations are going to actually occur? No one is actually deciding whether the ball is going to do reverse swing or will not based on whether continuum hypothesis is being valid or not. No one does that. But if you were to actually think of this as a rigorous fluid mechanics problem, you will see that we are safe treating it as a continuum problem. So this is something which you can work out, and once again you can try to compute what the spacing are, given that liquid water has a given density, has a molar mass and Avogadro number. You can find out what will be the volume per molecule and the mean intermolecular spacing. We'll work some of these problems out in the problem session for this week, and similarly you can actually also argue that in things like blood flow, where the lengths could be around microns, is it safe to assume continuum? So finally, as a lead on to our next lecture, we are going to think of fluid in a static state first, and the weight of air that is sitting on top of us has a weight of 10 tons per meter square, and we are not crushed. So the question is that, does the weight of the air, what does it do to our motion? And then thinking in terms of also quantities like viscosity, which is also going to come about in the next lecture. So this is some of the materials that the whatever I've discussed in this lecture is based on. So the primary textbooks are Fox and McDonald's and Pritchard's Introduction to Fluid Mechanics, primarily focusing on chapter 1 and 2, and Frank White's Fluid Mechanics chapter 1, and then there are a few other additional references for some of the aspects on the static structure of material, pitch drop experiment, and Deborah number. So with this, summarizing lecture 1, we saw that fluid mechanics upgrades our Newton's laws for rigid bodies to PDEs for fields on a deformable continuum. The phases of matter, they differ in the pair distribution function. They can be spikes for crystals, they can be these damped shells for liquids and a plateau for a gas. And the reason that this is happening, this arrangement is happening because of the competition between the well depth, intermolecular potential and thermal energy. A fluid cannot sustain shear stress at rest, it needs to flow. And the fact that whether you see a solid or a fluid in reality is observer dependent. So which is where the Deborah number comes in, the time scale over which you observe. Actually Deborah was a prophetess in the Old Testament, and the famous song that she sang, based on which Reiner came up with this number, is everything flows in the eye of the Lord. So even the mountains flows in the eye of the Lord. So something like a mountain, which is a solid block, will eventually flow, and that's something which is in consistence with what the geodynamics of mantles are. The continuum hypothesis averages over a volume containing many molecules, and the continuum framework applies beyond molecules, granular, active matter, flocks, and we are going to pick up on viscosity in the next lecture. What gives viscosity its molecular meaning, and then think of objects that have different kinds of viscosity. The first slide that I had in the picture, the background, was a fusion of two very famous paintings. One by Hokusai, which is the Great Wave picture, and the other is Vincent van Gogh's Starry Night. The reason why I chose these two pictures, because they are They're fascinating from a fluid mechanics point of view. People have actually studied them as fluid mechanics problem, even though the artist may necessarily not have thought of it that way. They have Hokusai's great wave has this fractal self-similar structure of the wave breaking. So people who have been interested in turbulence in terms of things going down to the smallest scales, they see beauty in this structure in terms of what the math reveals. And in the same way, the great wave, actually the right side picture is the fusion. The right side is the starry night and the great wave merged together. Starry night also people have thought in terms of what you see as those eddies in the sky as characterizing the scaling that you would observe in turbulence flow. So with that bit of art and fluid mechanics, we will close our first lecture and see you in next lecture.